Okay, going to be working 10.3, the dot product. And going to be starting with number 1, which I'll do 3 of these and then let you do the other 3. Number 1, part A, says you have a vector A dotted with a vector B and then dotted with a vector C, and it's asking you whether or not this has any meaning at all. So if you take a vector and dot it with a vector, you're going to get a number, which we'll say is a scalar. And then you're going to dot that with the vector. And the problem is that this dot is, a dot product, not a multiplication. So of course you can scale a vector if this were standard scalar multiplication, but it's a dot product. In order to do a dot product, we have to have 2 vectors. So we have a vector here and a number here. This operation is not possible. So that expression here makes no sense. That's what they're asking. Does the operation make sense? Is it doable? Let me look at B. So you have A dot B and then C like this. So notice that it's implied that there's multiplication here and it's not a dot. So it's implied that that's scalar multiplication. So let's see, we multiply these 2 together with the dot product and that's going to give us a scalar. And then we're going to take that scalar and we are going to multiply it times a vector C. So we're going to scale a vector. And so this does have meaning. This would be possible for us to compute. Let me give you an example next to this. Scalar, let's say you dot 2 vectors together, you get, let's say, the number 3. And then I say dot 3 with the vector 2, 4. This is not possible. Okay, so that's what this is saying. Here, let's say we dot 2 vectors together and we get 3. And then we scalar multiplication or scalar multiply 3 times this vector. That we can do. We just distribute that 3 through and we get the vector 6, 12. So very important to understand the difference between these 2 problems, A and B, is the dot product here versus scalar multiplication, which is implied because there's not a dot there. All right, and then we'll take a look at, we'll just do one more. Let me do F. So for F, we have the magnitude of a vector A dotted with the vector B plus the vector C. So you can see here again, the magnitude of a vector is going to be a number. So this is a scalar. And then we're dotting it with the sum of 2 vectors. When you add 2 vectors together, you get a new vector. I'll call it V. And so this is kind of like part A. You have a scalar, you're trying to dot it with a vector. That's not possible. So this would not make any sense. All right, I'll let you do the others. Now let's look at number 2. So we're going to find some dot products here. They give you a vector A is equal to the vector -2, 3. The vector B is equal to 0.7, 1.2. And we want to find A dot B. So all we have to do here is use our standard procedure for dot products. You take the first vector, 2, 3, to dot it with the vector 0.7, 1.2, you're going to get a number out. And what you do is you multiply -2 times 0.7, which is -1.4, and then you multiply 3 times 1.2, which is going to give you 3.6, and we add that to the first number we got, so 3.6. And then we add those two together, what do we get? 2.2. And that's it. So number 3 is pretty much the same way. Let me do number 5. So for number 5, you have two three-dimensional vectors. So we have the vector A, which is the vector 4, 1, 1/4. And the vector B, which is the vector 6, -3, -8. All right, so same thing, I want to find the dot product. So the dot product of these two vectors is equal to, we're going to multiply 4 times 6, which is going to give us 24. We're going to add to that what we get when we multiply 1 times -3, which is -3. So I'm adding a negative. I could have just written subtraction. And then 1/4 times -8 is -2. So I'm going to be adding -2. And then, so this is 24, take away 3, that's 21. Take away 2, this is 19. Okay, that was number 5. Let me see what's next. Let's look at 6. I'll go a little faster with 6. I'm not going to write down everything the way they are, or the way it, rewrite or write A and B. I'm just going to write, we're going to be doing the dot product for number 6. We're going to be dotting the vector P, -P, 2P, and we're dotting it with the vector 2Q, Q, -Q. So when we dot these two together, we get P times 2Q, which is 2PQ, plus -P times Q, which is, I'll change it to minus PQ. And then 2P times -Q is minus 2PQ. And then we clean this up. These are all like terms. They're all PQ, P times Q. So these two cancel actually. And all you're left with is -P times Q. All right, number 8. Let's look at 8. I'm skipping 7. So you need to first be able to, on number 8, convert this this I hat, J hat, K hat notation. So they give you the vector A is 3I plus 2J minus K. And they give you the vector B is equal to 4I plus 5K. So convert A over first. This is the vector. We just look at the numbers in front of I, J, K. So 3, 2, -1. And B, this vector is the vector 4. And since there's nothing in front of the J, there is no J, there's a 0 there, and then 5. And so we can now take the dot product. So A dot B will be equal to, we're going to multiply 3 times 4, which is 12. Then add to that 2 times 0, which is 0. Then -1 times 5, which is -5. And that gives us 7. All right, moving along. Let's look at number 9. So number 9, we're told that the magnitude of the vector A is 6. we're given that the magnitude of the vector b is 5. And we're given that the angle between these, I'm going to call it theta, is 2 pi over 3. And we're asked to find the dot product. So. Come to the door. Okay, so to do this problem, we're going to use the fact that A dot B is also the magnitude of A times magnitude of B times cosine of the angle between the two vectors. So if we're given the vectors in the component form, right? So with the angled brackets and we get the components, we do what we did in the previous problems. But if instead we have the magnitudes, the lengths of the vectors and the angle between them, then there's also a way we can compute the dot product using this formula. Oops, that's supposed to be B. All right, so this will be pretty clean. It's just going to be the magnitude of A, which we know is 6, times magnitude of B, which we know is 5, and then cosine of 2 pi over 3. Now this is 30. And then let's talk about cosine of 2 pi over 3. And just go back to your unit circle. You know, where is 2 pi over 3? So here's pi over 3 up here. All right, that's going to be, what, 60 degrees? And then 2 pi over 3 is right here. And when you say cosine of 2 pi over 3, you're looking for the x-coordinate here. The x-coordinate there is -1/2. Remember, the y-coordinate is √3 over 2. So we're going to use -1/2. So it's this times -1/2, which is going to be 15, -15. And that was number 9. Number 10 is done the same way, except that the angle is 45 degrees. So yeah, I'll let you mess with that one. All right, let's look at 11. 11's somewhat interesting. So 11, it says if u is a unit vector, so they're telling you that u is a unit vector. That means the length of u is 1, so you're given that. They want you to find u dot v and then find u dot w, and they give you a picture. All right, so here's a picture. They give you this triangular shape, this. They give you these little dash marks like this. They tell you this is u, they tell you this is v, they tell you this is w right here. And u is the vector going from here to here, so that's u. And then w is the vector going from here to here, so I'm putting an arrow like that. And then v is the vector that goes from the top down to the bottom. So I hope you can see those arrows. I'll kind of exaggerate them a little bit. All right, there's u, there's v, there's w. Well, one thing we should notice is that if they have these little dashes on the sides, that means this is an equilateral triangle, which means all the lengths of the vectors are the same. So that means that the magnitude of v is also 1, and the magnitude of w is also 1. So that's good to know. And if we want to find u dot v, and we know the magnitudes of each of the vectors, 1 and 1, I can use, it might make sense for us to use this formula, cosine theta, where theta is the angle between the two vectors. So coming up here and looking at u and looking at v, okay, if we attach their tails together like this, we're just trying to figure out what this angle is. Well, that angle is pretty easy because this is an equilateral triangle. That should be 60 degrees. So we should get 1 times cosine of 60 degrees. Cosine of 60 degrees, back to that unit circle. 60 degrees is up here. Cosine's the x-coordinate, which is 1/2. So this should just be 1 times 1 times 1/2, which is 1/2. So u dot v is 1/2. And now we need to look at the next one, which would be trying to find u dot w. So let's see what u dot w looks like. So u dot w should be the magnitude of u times the magnitude of w times cosine, I'm going to say, of beta, where beta is the angle between them. So theta was here, right? So now we're going to look at u and w, and this is a little bit tricky, all right? Because before you can talk about the angle between the two vectors, you have to attach their tails together. So this vector u, the tail's up here, the vector w, the tail's back here. So I need to slide u down like this in order to be able to talk about the angle. So imagine that this is w. I'd slide u down like this. U would go like this. And we're trying to find this angle here, which we'll call beta. Now, extending this up like this, we know that that created that triangle. We know that this is 60 degrees. And if that's 60 degrees, then a full rotation, okay, this way is 180. That means this beta would have to be 120. So the angle between u and w is actually 120, not 60. So be careful with that here. The direction of the arrows is going to dictate that and where the tails are. So going back to this formula right here, I know that the magnitude of u was 1 times the magnitude of w, which is 1, and then cosine of 120 degrees. And you can look at your unit circle. This is going to be negative 1/2. So the answer here is negative 1/2. Cosine of 120 is negative 1/2. All right, let's look at 13. I think I'll do, there's part A and part B. Maybe I'll do just part A. Let me do it first and see if that's enough. So for 13, part A, show that I dot j equals j dot k equals k dot I, oops, equals 0. So you're going to try and show that I hat j hat dot j hat equals 0, that j hat dot k hat is equal to 0, and k hat dot I hat is equal to 0. So let's start with this first one. I hat, by definition, is this vector 1, 0, 0. I'm going to dot that with j hat, which is 0, 1, 0. All right, so I'm just doing this one right here. And if I dot those, I do 1 times 0, which is 0, plus I do 0 times 1, which is 0, and I do 0 times 0, which is 0, and that's 0. So far it checks. The first one's true. Now let's do j hat dot k hat. So j hat is 0, 1, 0. Dotting that with k hat. which is going to be 0, 0, 1. And when I dot, 0 times 0 is 0, plus 1 times 0, which is 0, plus 0 times 1, which is 0, which is 0, that checks. And then k hat dot I hat would be 0, 0, 1, dotted with I hat, which is 1, 0, 0. And therefore, you do this, you'll get 0 also. All right, not bad. Okay, so let's look at part B. Part B says to show that I hat dot I hat equals j hat dot j hat equals k hat dot k hat equals 1. So I'm just going to do one of these. I'm just going to do this one right here. I'm going to show that that's equal to 1. So if I take I hat, that's 1, 0, 0. I dot it with itself, 1, 0, 0. Then I get 1 times 1 is 1, plus, and then 0 times 0, 0, 0 times 0, 0, so plus 0, that equals 1, that checks. And you can do the rest. All right, let's look at 14. 14 looks like a word problem. It says, a street vendor sells A hamburgers. So A is the number of hamburgers that are sold. B hot dogs. And C is the number of soft drinks. I'm just going to put number of drinks. He charges $2 for a hamburger. I'm just going to put an arrow here. $2 each. Charges $1.50 for a hot dog. And charges $1 for a drink. If the vector A equals ABC, and the vector P equals 2, 1.5, 1. What is A dot P? So recognize that ABC are the number of hamburgers, hot dogs, and drinks respectively, and 2, 1.51 are the costs corresponding to the hamburger, hot dog, and drink. So if I dot these two vectors together, I'm going to do A times 2, which is 2A. Do B times 1.5 and add it, so 1.5B. Plus C times 1, which is C. And what would that quantity represent? What would A dot P mean to us? This would be the total revenue for the person selling these things, right? So if somebody tells me how many hamburgers, hot dogs, and drinks I sold, then that formula right there would give me all the money that I brought in. So this would be the revenue. The money that you bring in. It's kind of an interesting, all they're trying to do is get you to see that you can take this problem and that the dot product can actually represent something here rather than just some arbitrary number that comes out at the end. All right, number 15. Find the angles between these vectors. Was that 12? Hold on. That was 14, sorry, yeah, I think I forgot to change it. That was supposed to be 14. So 15 is what I'm working on now. got some vectors here. You've got A, vector 4, 3. B is the vector 2, 1, 2, negative 1. And we're supposed to find the angle between these two vectors. All right, so I'm going to need my calculator for this. All right, clear everything out. All right, so we have a formula, right? We have a formula for this. The angle between two vectors, right? If we're given two vectors A and let's say another vector B, the angle between them is equal to cosine inverse, or the arc cosine, of A dot B divided by the magnitude of A times the magnitude of B. So that's our formula. So I'm just going to see what I need here. I'm going to need to do A dot B. Okay, I'm going to figure that. But I'm also going to need the length of A and the length of B. So let me work on those right now. The length of A is the square root of the sum of the square of the components. So I'm going to square 4, get 16. I'm going to square 3, get 9. Add these together. Square root of 25 is 5. So the length of A is 5. The length of B is the square root of, let's see, 2 squared, 4. Negative 1 squared is 1, so root 5. And let's figure out what A dot B is. So multiply the components. 4 times 2 is 8. Add to that this, but that's negative 3, so subtract 3, we get 5. So here's what we've got. In this formula, theta will be equal to arc cosine of A dot B, which was 5, over magnitude of A, which was 5, times magnitude of B, which was root 5, which is the same as arc cosine of 1 over root 5. So I'll go ahead and do that on my calculator. 1 divided by, 1 divided by the square root of 5, and then take the inverse cosine of that. I'm getting theta is, and I'm in radians here, 1.107 radians, which if we convert that to degrees, we multiply by 180, we divide by pi, and we should get 63.4 degrees. All right. That's it. Now, I think the rest of these, number 16 and 17, are pretty much the same, except they're three-dimensional vectors. I'll let you mess with that. I think you can handle that. I think 18's worth looking at. Because when I do 18, you'll know how to do, I'll have to do the same thing I did for 16 and 17. So 18 should be enough to cover that material. So it says find correct to the nearest degree the three angles of this triangle. So they give you a triangle and they give you vertices. So you don't need to do this, but I'm just going to do it for fun. Try and draw this. You go out, let's see, 1, 0, negative 1. That's A. 3, 1, 2, 3, negative 2. and then 0, that's here, and then 1, 3, coming this way. So maybe like 1, 2, 3, and then up 3, somewhere around there. Okay, so we've got these 3 points in 3-dimensional space. I'm only doing this just to help you see it. So this point here is in the first octant. This is C. A, this was B. Okay, B was flat. It was on the XY plane because we never went anywhere on Z. All right, that's good enough. So there are 3 points in space. We connect them with lines. And when we do that, we create a triangle. So it's important to note that these are points in 3-dimensional space. These are not vectors. And we're asked to find the angles of this triangle. And to do that would be very difficult without the dot product. So I'm going to erase everything here. And just draw my triangle like this. A, B, and C. And what I'm going to do is I'm going to create some vectors. So let's try and get this angle right here first, which we'll call little a. All right. To get little a, we're going to need to get 2 vectors. We're going to need to get the vector going from here to here. That's the vector that's going from A to B. And then we're going to need to get the vector that goes from here to here. That's the vector AC. And if I can get those 2 vectors, then I can talk about the angle between them. So let's go ahead and write down what those are. The vector from A to B, we use the points here, right? I'm going to take all the B coordinates of the point and subtract all the A coordinates because I'm going from A to B. So 3 minus 1 is 2. That's a vector, 2. Negative 2 minus 0 is negative 2. And 0 minus negative 1 is 1. So this vector AB, right, is the vector 2, negative 2, 1. Then the vector from A to C, I'm going to do the C coordinates and subtract the A coordinates. So the vector from A to C is, let's see, 1. Take away 1, you get 0. 3, take away 0, you get 3. And then 3, take away negative 1, you get 4. So this is the vector 0, 3, 4. So if I want to now know the angle A, I'm going to use that inverse cosine formula. The angle A in this problem will be equal to arc cosine of this vector dotted with this vector, so AB dotted with AC, over the magnitude of this vector, AB, times the magnitude of this vector, AC. So let's do it. I need to figure out what AB, the vector AB dotted with vector AC is. I'll figure that out in a second. I need the magnitudes also. So let me get the magnitudes, and I think I'll do the magnitudes right here. The magnitude AB is going to be these components squared and then square root. So square root of 2 squared is 4 plus negative 2 squared is 4, and then 1 squared is 1. So you get square root of 9, which is 3. And then the magnitude of AC, which is this vector, we need that, is square root of this squared plus this squared plus this squared. So we have 0 plus 9 plus 16. That's square root of 25, that's 5. And then we need the dot product. So we take AB, B, and dot it with AC. We get, now we're just multiplying 2 times 0, 0. Negative 2 times 3 is negative 6. 1 times 4 is 4. So this is negative 2. And so now I think we have everything we need. The angle A, will be equal to arc cosine of AB dotted with AC, which we said was negative 2, over the magnitude of AB, which was 3, times the magnitude of AC, which was 5. And so this is cosine inverse of 2/15. So I get my calculator out again. 2/15, I take the inverse cosine of that, and I get that this angle A is equal to 1.437 radians. And did they want it in degrees? Yes, in degrees. So times 180 divided by pi is 82.34 degrees. And they want it to the nearest degree, so I'm thinking they're going to want you to put 82 degrees. Let's see, what number was this? This was number 18. Oh, you know what? I know what happened. I forgot my negative. Oops, negative. Clear that. Negative 2 up here. So negative 2 divided by 15, arc cosine. Yeah, apologies. This should be little things, 1.70 radians. And then times 180 divided by pi. All right, that's better. 97.66 degrees, which is approximately 98 degrees. So that's one of the angles. Now you have to go get another one. Once you get 2 of them, you can find the third one because they all have to add up to be 180. But to do, let's say, this angle B, you'd have to start things over, I guess. Well, not really. But you would need 2 new vectors. It would be the vector going from here to here. So you'd need BC. And you need to be working with the vector going from here to here, which would be the angle BA. So the vector BA would be easy to get because it's just the opposite of this one. It's pointing in the opposite direction. So it's just negative 2, positive 2, negative 1. But you need to get BC. And then you do the whole thing again. So I'm not going to do that. I'm just going to tell you what the other angles are. The other angles of this triangle should be 54 degrees and 28 degrees. So once you go through and work this again, you should get 54 degrees and 28 degrees. And that'll be it. How are we doing here? Number 19. All right, so for number 19, it asks whether these vectors are orthogonal, parallel, or neither. So let's say they give you the vector A. There's different parts to this. I'm doing part A right now. A is negative 5, 3, and 7. And then vector B is the vector 6, negative 8, and 2. So the question is, are these orthogonal? Are they parallel? Or neither? So what does it mean to be orthogonal? Orthogonal means that A dot B would have to be 0. Parallel would mean that A must be some scalar multiple, C, times the vector B. So there has to be a way to just multiply B by a number, the vector B by a number, scale it, and get A. And then neither would be if those two things are not true. So let's look at the orthogonal first. Are these orthogonal? So what's A dot B? Well, this is going to be negative 5 times 6 is negative 30, plus 3 times negative 8, which is going to give me negative 24. And then 7 times 2 is 14. I think that that's obvious. That's not equal to 0. So they are not orthogonal. Are they parallel? Well, what we need to do is we need to see if there's a way to turn negative 5, multiply it by something to get 6. Well, what do you have to multiply negative 5 by? Multiply it by something, I'm going to call it C, to get 6. Well, C then would have to be negative 6/5. So if I multiply negative 5 times negative 6/5, I would get positive 6. But that C has to work for every one of these. So if I multiply the 3 by that negative 6/5, am I going to get negative 8? That's the question. So let's try it. Negative 18 over 5, that's not negative 8. No, that's not going to work. So there's no way to just multiply this vector, scale it by a number, and get that vector. So they're not parallel. And since they're not orthogonal and they're not parallel, the answer is that they're neither. Okay, so how about part B? The vector 4, 6, and negative 3, 2. Well, you know what? I think that that's too easy. I mean, you can work that yourself. You get the idea of what you're supposed to be doing here. I think 20 works the same way. And I'm looking at my time here, how much time I've got left. I think 19 you can do the rest, and 20 you can do. Let me do one where they're parallel so you can see parallel. How about 19D? So 19D, you're given two vectors. A is the vector, I'm going to convert it right now. It's 2, 6, negative 4. B is the vector negative 3, negative 9, 6. So do a quick dot product, okay, to see if they're orthogonal. So A dot B, so I get negative 6, I get negative 54, negative 24. There's no way that's 0. So they're not orthogonal. To see if they're parallel, let me first try and turn 2 into negative 3. So if I'm going to multiply 2 by some scalar to get negative 3, then that scalar must be negative 3/2, just dividing by 2. So that's how I can turn 2 into negative 3. So the question is, am I going to be able to turn 6 into negative 9 if I multiply by the same scalar, negative 3/2? And you can see here that if you do this, right, you get negative 18 over 2, and that is negative 9, and that works. So I know I'm going to be able to turn the 6 into a negative 9, and then I need to check, can I turn the negative 4 into 6 also? So by scaling by the same thing, negative 3/2. And check it yourself, that's 12 over 2, that's 6, that works. So they are parallel because they are scalar multiples of one another. In fact, if you take the vector A, right, and you scale it by negative 3/2, you get the vector B. That's what we just said. Take this, multiply it by -3/2, it'll turn into this. You could have also done it the other way around. You could have tried to turn this one into this one. If you did that, you would have gotten this. A is equal to -2/3 B. So just algebraically, if you multiply both sides by the reciprocal here, then that's what you would have needed to go the other direction. So, all right, hope that makes sense. All right, I think I'm going to do a quick stop right now and then come back, pick up the rest of these problems. Okay, so I'm going to assume you can do 20 on your own. Number 21. I'm just going to tell you how you would set up 21. For 21, they give you 3 points that create a triangle. And you're trying to decide if this is a right triangle or not. So what you do is you have to find some angles. Or, I mean, that's one way you could do it. You could say, all right, let me try and find the angles and try and see if one of them is 90. You could also create vectors, right? If this is a right triangle, at least one of these is 90. If this is 90, then these two vectors are orthogonal. So if you create this vector, and dot them and get 0, you know you have a right triangle. So let's say you create two vectors, you dot them, you don't get 0. Then what you do is you would take two more vectors, this one and this one, to try and figure out this angle, dot those two together, see if you get 0. If you don't, then you still don't have a right triangle. And then you would take this vector and dot those and hope to get 0. So that's probably the cleanest, fastest way to do the problem, is just to do this combination of figuring out vectors, dotting them, and looking to see if you get 0. If you never get 0, it's not a right triangle. All right, so let's look at 22. 22 is a little more involved. So it says, find the values of x such that the angle between these vectors, 2, 1, -1, and the vector 1, x, 0 is 45 degrees. Okay, so they want to know if I make this, if I give you a value of x here, like let's say 5, then will the angle between them be 45 degrees? And we need to figure out all values of x that would make the angle between these 45 degrees. So it's kind of interesting. If you look at it three-dimensionally, you have a vector sitting out here. This one's not moving. It's right there. This vector has some certain conditions. The x component is 1, the y component is 0, and the z component is free to be whatever we want. So maybe there's a way that we can find some vectors that'll always make an angle of 45 degrees with this vector. And so which ones do it? So what does it mean for it to be 45 degrees? Well, several ways we could look at this. We know this formula, A dot B must equal magnitude of A times magnitude of B, cosine of the angle between the vectors. We know that equation. We call this vector A, we call this vector B. What would A dot B turn out to be? So if I multiply or dot product these two, 2 times 1 is 2, plus 1 times x, which is x, -1 times 0 is 0. So left side of that equation would be that. All right, the magnitude of A I can figure out. So square this is 4, square that's 1, square that's 1. So I'm doing 4 plus 1 plus 1. That's 6, and then take the square root. So I have root 6. And then the magnitude of B, so square that 1, square that x squared, square that 0. So I have 1 plus x squared underneath the square root. And then cosine of 45, I multiply, because I need it to be 45 degrees, cosine of 45 degrees will be root 2 over 2. So this is an equation that has the variable x in it. So let's clean it up a little bit. Okay, the left side is just 2 plus x. I'll just put x plus 2 instead. Equals, over here, how should we do this? Let's go ahead and, I'm trying to figure out how I want to mess with these roots. How about we put the root 2 times root 6, make it root 12. So I have root 12 over, there's a 2 here, 2. And then this, which is root 1 plus x squared, like that. So that's the right side. And I need to try and solve this for x. So when I solve this for x, what I'll do is I'll try and free this x squared from the radical. So I'm going to square both sides of the equation at this point. Square this side, square that side. I'll get over here x squared plus 4x plus 4. So just multiply that out. And then over here, when I square, since it's multiplication, I square this and then square this. So I get 12 over 4, which is 3, right? Square top 12, square the bottom is 4. And then I square this square root, I get 1 plus x squared. And what I'll do is I'll distribute the 3 through now. I have a quadratic equation. So I'm going to bring everything to one side. So I'm going to make this side 0. I'm going to have 3x squared, but I'm going to take an x squared away, so 2x squared. I'm going to bring the 4x over, so negative 4x. And then I'm going to subtract 4 on both sides, so minus 1. And then from there, I'm going to use a quadratic formula. Okay, so when I use a quadratic formula on this, it's not going to factor. I get x is equal to negative b, which is 4, plus or minus the square root of b squared, which is 16, minus 4 times a, which is 2, times c, which is negative 1, all over 2 times a, which is 2. So that's our quadratic formula. And we should get, hopefully, a couple of answers here. 4 plus or minus the square root of, let's see, this is going to be 8, negative 8, but we're subtracting, so plus 16 plus 8, that's going to be 24, all over 4. And what can I do here? I can pull out, I can pull out a 2 out of there, right? So this is 6 times 4, so square root of 4 comes out as a 2, root 6, all over 4. And so I get, reduce everything by a factor of 2. We get 2 plus or minus root 6 over 2. And that's 2 potential answers. Now I need to check these. The reason I need to check them is because it could be possible that I have an extraneous solution because I squared, and anytime you square an equation, you could potentially introduce a solution that doesn't work. So what I would need to do to check this is I need to take the vector, the original vector, which was 2, 1, negative 1. That's my A. And then my B is the vector 1 and then x, which I just found to be 2 plus or minus root 6 over 2. And then 0. This is B. And I need to check that the angle between those is 45. So I'd have to check both the positive and the negative case. So let's just take the positive case, and I'll let you check the negative on your own. What's the angle between those vectors? Well, the angle between those vectors is the inverse cosine of A dot B. So let me try and do A dot B quickly. 2 times 1 is 2, plus 1 times this. So 2 plus root 6 over 2. that's A dot B, over the magnitude of A. So the magnitude of this is this squared, 4 plus 1 plus 1. So that was root 6. The magnitude of this one, which is that squared, this squared, 1, plus, now we have to square this, and that's going to be a little tricky. I know the bottom of it is 4. The top of it, though, is this squared. 2 plus root 6 times 2 plus root 6, which is 4 plus 4 root 6 plus 6, which is 10 plus 4 root 6. So we could put that in there. That's going to be just the top. So this is 10 plus 4 root 6, and then plus this one squared, which is 0. So this is kind of an ugly number here. 1 plus 10 plus 4 root 6 over 4. And so I need to get my calculator out, and I need to do that. Am I going to do it? Do I feel like doing it? I'm using my phone. If I had my calculator, I'd feel better about this. Using the phone to do it's a little harder. Let me try it. Okay, I'm going to do 6 root plus 2 divided by 2 plus 2. So this whole top here, I'm getting 4.2247 over, now let me try and do this. 6 root times 4 plus 10 divided by 4 plus 1 square root times 6 root. I'm getting 5.974, something like that. And I'm going to take cosine inverse of this. So let me try that. 4.2247 divided by 5.974. And then arc cosine, times 180 divided by pi. I'm getting approximately 44.9939 degrees. Close enough. So there's some rounding error in there. So it did work. So using a plus here worked. You would have to check to see if the minus works. It also works. I'm not going to show it. So interesting problem. 23. Had to cut out there real quick. Gonna pick up where I left off. I believe number 23 is where I am. So 23, interesting problem. It says find a unit vector that is orthogonal to I hat plus j hat and I hat plus k hat. So I need to come up with a vector, three-dimensional vector. I'll call it u, which will be labeled u1, u2, u3, the components. I need this vector to be orthogonal to this and to this. So let's call this vector v, this vector w, and let's figure out what those are. V is I hat plus j hat, which means that it's just 1, 1, 0. And then w is I hat plus k hat, which is just the vector 1, 0, 1. So I'm trying to figure out if I can find a vector called u that is a unit vector that is orthogonal to both of those. So let me start with the orthogonality. I need that u dot v is 0. Okay, that's what I need. So I need that when I dot these two together, I get 0. So if I dot this with this, I just get u1 plus u2 plus 0, because the last component is 0. That equals 0. So that means that u1, if I move things around here, must equal negative u2. All right, I also need that u dotted with w must be 0. So when I dot this with this, I get u1 plus 0 plus u3 must be 0. And solving for u1 again, I get u1 must equal negative u3. All right, so here's what I have so far. I have that in order for this to work, my u1 must be equal to negative u2, but it also must be equal to negative u3. So these two have to be exactly the same, and this has to be different in sign. So if I go back to my u, I'm going to say, okay, u1 is just going to be some number, right? And then u2 will be the opposite of that number. Okay, so just imagine moving the negative to the other side. u2 would be negative u1. And then over here, ignore this, move the negative to the other side. u3 must be negative u1 also. So far, that's what I'm going to need for the orthogonality to work out, for the dot products to be 0. But then I also need that this be a unit vector. So I want also the magnitude of u to be equal to 1. And the magnitude of u will be this squared plus this squared plus this squared. Since they're all u1s, and I'm squaring so the negative doesn't matter, I'm going to get u1 squared plus u1 squared plus u1 squared must be 1, which means that the square root of 3u1 squared must be equal to 1. Just add them together. And this means root 3 times root u1 squared must be 1. Right? And if I go and say, then this right here means that the absolute value of u1 must be equal to, I just divide by root 3, 1 over root 3. So I could have this. I could have u1 be equal to positive 1 over root 3, or I could have u1 be equal to negative 1 over root 3. In either case, I should get a magnitude of this vector to be 1. So I think I'm ready. I'm ready to write down what u should be. Let's first start off and say u is equal to, let's let u1 be 1 over root 3. And then the u2 should be the opposite of that, the negative, and the u3 should be the same as the second component. So that's one potential answer. Or you could have done negative 1 over root 3 and then change the sign positive and positive. And I'll leave it for you to check yourself. But if you take this and you dot it with this and dot it with this, you should get 0. And the magnitude of this vector is 1. Same thing here. If you dot this with this and then dot it with this, both of those should give you 0. And the magnitude of this vector is 1 also. So kind of an interesting problem there. All right, that was 23. 24. Find two unit vectors. So I want to find two unit vectors that make an angle of 60 degrees with the vector v is 3, 4. Now this is two-dimensional, so I should be able to draw this. So here's the vector 3, 4. That's the vector v. I'm trying to come up with two vectors that form an angle of 60 degrees with this. So there should be another one, 60 degrees this way, and another one 60 degrees this way. Find those two vectors and make sure that they're unit vectors. So let's start out by talking about what one of these vectors would look like. So I'll call it u. So I'm thinking u somewhere over here, okay, u. But it's a unit vector, so it's probably not that long. It's probably going to need to be somewhere down in here like this. I need to come up with that. Well, let's just call it u1, u2. And what are some things we know about this? Well, the angle has to be 60 degrees between these. So I know that u dotted with v must equal magnitude of u times magnitude of v cosine of 60 degrees. I know that much. If I dot these two vectors together, I get 3u1 plus 4u2 must equal the magnitude of u. Well, I want this to be a unit vector, so I know that that length is going to have to be 1. And then v, the magnitude of this, if I do my little square root, square each one, I should get 5. And then cosine of 60 degrees is 1/2. So that tells me that, so far, trying to find my u, I know that 3u1 plus 4u2 must equal 5/2, right? It's multiplying out the right side. And the other condition I had here that I haven't looked at was that u1, magnitude of u had to be 1, right? So let's go ahead and let's rewrite this and let's find its magnitude. The magnitude of u, do it right here. The magnitude of u is the square root of u1 squared plus u2 squared. That needs to be equal to 1. See, I have an equation though that contains u1 and u2, so I can solve this equation for, let's solve it for u2. We'll replace that in here, and then we'll have an equation with just u1 in it, and I should be able to solve it. So solve this for u2. You get 4u2 equals negative 3u1 plus 5/2, which means that u2 is equal to negative 3/4 u1 divided by 4 plus 5/8. All right. So coming here, I'm going to rewrite this equation right here. I need this to be true. I know what u2 is. I'm going to leave u1 as u1. So this becomes square root of u1 squared plus, now I'm going to have this in here, negative 3/4 u1 plus 5/8 squared. That must equal 1. And I'm going to continue to work that problem right here. So this is a quadratic, well, it's a radical equation, but it has u1 is squared here, and u1 I'm going to wind up squaring. I need to actually expand that out. So let me go ahead and do that over here. What's negative 3/4 u1 plus 5/8 times itself? Negative 3/4 u1 plus 5/8. So here to here, you get 9/16 u1 squared. Let's see, here to here, what do we get? Negative, it's going to be a negative number, negative 15 over 32 u1. And then when I do the middle one, I get the same exact thing, negative 15 over 32 u1. And then the last multiplication plus 25 over 64. And then I can put these two together. That's negative 30 over 32 u1, which is, reduce everything out, 15/16 u1, negative. Okay, so coming back there, I think I can erase this now. We have that the square root of u1 squared plus this squared, which we just turned out to be 9/16 u1 squared minus 15/16 u1 plus 25/64 all under the root, that must equal 1. And I can start putting this stuff together. Well, let's square both sides. We square both sides and the root goes away. 1 squared is still 1. So now put these two together, get a common denominator. You should get 25/16 u1 squared. So I just combine those two. And then minus 15/16 u1 plus 25/64 equals 1. And I'll subtract 1 from both sides here. So if I subtract 1, what will happen here is I'll get minus 1 equals 0. And then I can rewrite 1 as 64/64. That way I can put those together. If you take 25 away from, oh, I'm sorry, if you take 25 and subtract 64, what do you get there? 40, can't do my simple math again. 29? So 25/16 u1 squared minus 15/16 u1 minus 29/64 equals 0. All right. Okay, so now this is a quadratic equation, so you could solve it. There's two solutions. I'm going to, before I go to quadratic formula, I'm going to just clear the fractions. So I'm going to multiply everything by 64. So when I multiply this by 64, this by 64, this by 64, that doesn't matter. We should get, so 64 divided by 16 is 4, right? It goes in there 4 times. Then times 25, so you get 100 u1 squared. Again, 16 goes to 64 4 times. 4 times 15 is 60, so minus 60 u1. And then over here, the 64's cancel, so minus 29 equals 0. And you know what? Oh my gosh. Okay, sorry, 39. Oops. See, simple arithmetic. 39, look, 64, take away 25, right here, borrow 5, 3, 9. I know, okay, it's Cal 3, I should know how to do that, but my brain just doesn't like to work on basic arithmetic anymore. I'm not sure why it doesn't like it, but it doesn't. So this minus this should have been negative 39, not 29. That's going to change that. 39. Bah. All right, so you use your quadratic formula. And I'll just tell you what we get for the answers here. You get u1 after you simplify is equal to 3 plus or minus 4 root 3 all over 10, which is approximately, well, there's 2 different answers here, so I'll give you both answers. One answer is, if you convert it to a decimal, 0.9928. And if you convert the other one to a decimal using subtraction, negative 0.3928. So that's what your U should be, your U1 should be. And remember, we had an equation for U2. We had solved for U2 a while back. And so here's what we've got. U should be equal to the vector 0.9928. And then you have to go compute what U2 is. Go back and look at our equation for U2. plug this in for U1, and then when you do that, you should get negative 0.1196. And then if you do the other option, would be to let my U1 be negative 0.3928, and then if you go solve that one for U2, you should get 0.9196. Okay, so let's take a look at those. 0.9, this one right here, 0.9928 is here, and then down 0.1, so it's really close, like right in there, just down a little bit. That vector right there should be a unit vector and have an angle of 60 degrees. This one, here's negative 1, negative 0.39, so about right there. Go up about 0.91, somewhere in here. This vector should have unit length and should also form 60-degree angle right there. So that's it. That's how you work that one. Sorry about that 39. You're probably watching the video going, duh, should have been 39. Okay. Where are we? 25. So for 25, it gives you two lines, two equations of two lines here. 2x minus y equals 3, and 3x plus y equals 7. And it's asking us to find the acute angle between these lines. So these are two-dimensional lines, so I'm gonna graph them for us. If we take this equation right here, we solve for y, we get y is 2x minus 3. So that's what this becomes. This one we solve for y, we get y equals negative 3x plus 7. That'll make it easy for me to graph. This first one, I start negative 3. And then from there, I go use the slope 2 over 1. So up 2 to the right 1. And then I could do it again. I could go up 2 to the right 1. And I've got some points there. I don't have a straight edge in here. I used to have a ruler in here. Close enough. So that's one line. The other line, I start at 7. 3, 4, 5, 6, 7, right? And from that point, I use the slope negative 3 over 1, so that's down 3, 1, 2, 3 to the right 1. And then down 3, 1, 2, 3 to the right 1. Oh, they actually hit right there. So, like this. And what we're trying to do is we're trying to find the acute angle between these two lines. So the smallest angle between these two lines, which would be like this angle. We want to know what that is. Well, what we could do is we could just use as a reference this point and then start by trying to figure out, like, what is this vector right here? Or what is a vector that would point in the same direction as this one? Well, that corresponds to the slope of the line, right? The slope of the line is 2, which is 2 over 1. So if I look at this as a vector, I could say, let me call that vector u. It's going to be equivalent to the vector, or the vector 2, 1, right? Sorry, got that backwards. 1, 2. Slope is 2. So 1, 2. So to the right 1, up 2, right, would be running parallel to this line. And then let me do the same thing. Since this is a negative slope, I'm going to have to look at the vector that goes like this, okay? And the slope of that one is negative 3. So a vector that would be parallel running in the same direction would be the vector, let's see, we go to the right 1 down 3, so right 1 down 3. So if I can find the angle between those two vectors, it would be this angle. I know that, you know, all the way from here around is 180. So if I just take 180, subtract this angle, that would give me this one. So let's find the angle between those two vectors. So I'm actually going to be finding right now this angle, which is theta. And what I know is that theta is equal to cosine inverse of the dot product of these two vectors. So that's 1 minus 6, so negative 5, over the length of this vector, which is the square root of 5, and the length of this vector, which is the square root of 10. And then I get on my calculator and compute that. So let me just take a look here. What number was this? 25? Yeah, that's good. And then if you do this on your calculator, you'll get theta is 135 degrees. But that's theta. We want this one, beta. We know that theta plus beta is 180. So we know beta plus theta is 180. That means beta plus 135 is 180. So that means beta is what? 45 degrees. So that's the acute angle, the smallest angle between those two lines. Now 26 works pretty much the same way. All right, so what else do we have on our list here? 31. Find the scalar and vector projections of B onto A. So for 31, they give you a vector, vector A. Let's see how much time, oh, like 9 minutes. 3, 6, negative 2. The vector B, which is 1, 2, 3. And they want to find the scalar and vector projections. So we have two formulas here. The scalar projection, and they want B onto A. All right. So the scalar projection is equal to what we call the component of the vector B onto the vector A, which I gave in class is just A dot B over magnitude A. And then the projection we'll do afterward. Okay, so the vector projection. So we need to dot these two. So let's dot them. You get 3 plus 12 minus 6 over the magnitude of A, which is the square root of all the components squared. So 9 plus 36 plus 4. So you have on top 9, on the bottom, what's that, 45, 49, square root of 49 is 7. So 9/7. This is for 31. 9/7. All right, and that's it. And then let's do the vector projection. So the vector projection is going to be equal to, we call it the projection B onto A. So we have a formula for this, very similar to the last formula. It's A dot B over magnitude of A, very similar, but then squared and then dotted with the vector A. So a lot of this we already have. We have A dot B, which we knew was 9. The magnitude of A was 7, but we square it, so 49. and then dot that, sorry, I said dot, damn it, scalar multiple. We multiply that times the vector A, which is 3, 6, -2. And so just distribute through, and you're there. 27/49, 54/49, -18/49. Okay. So remember, this is a vector, that's a number. So when you take a vector B and you project it onto a vector A, which is what we just did, you're dropping a perpendicular down, you're coming up with this vector right here. The length of this vector is 9/7. The actual coordinates or components of the vector itself is this 27/49, 54/49, and -18/49. So that vector is the actual red vector. That number is the length of it. All right, 31, what else? 35. All right, so 35 is a little bit weird. They give you a vector. It says if A is equal to the vector 3, 0, -1, find B, find a vector B such that this is true. So that means the scalar projection is 2. So the length of it is 2. So we've got some vector that's given to us right here. We need to find a vector that when we project it onto this, the length of it is 2. That's what this is saying. So let's set up the left side of this, right? This is A dot B over magnitude of A. We need that to be equal to 2. So that's what we know. Now B, we don't know what it is. We have to find it. So let's call it B1, B2, B3. And let's talk about what A dot B would be. So if I dot that with that, I would get, let's see, 3B1, and B2 times 0 is gone, so minus B3. That's the dot product on top, over the magnitude of A. The magnitude of A is the square root of, we've got to just do the square of those components. So 9, 0 doesn't matter, plus 1. We need that to be equal to 2. And then 3B1 minus B3 must equal, this is root 10. And just multiply both sides by root 10. So 2 root 10. That's all. I mean, right now we have a lot of freedom. We need to find a vector that satisfies this, but we have one equation and 2 unknowns, so that means there's an infinite number of solutions. So we know what they need to look like though, right? Let me see. I have my vector B so far. B1 can be whatever I want. B2 doesn't look like it matters because when I dot it with A, remember A was this? 3, 0, -1. When I dot these two together, that times 0 is not going to matter. So B2 is free to be whatever I want. And then B3, I could solve this for B3. So I could get like 3B1 minus 2 root 10. That's what you would get if you solve this for B3. So if I pick a vector that looks like that, it should satisfy everything that we want. So let's just pick some values. Let's let B1 be equal to 1. You know what? We'll be clever here. Let's let B1 be root 10. Because if I do that, then it's going to be easy to calculate. Let's let B2 be 0. So what would B look like then? B would be root 10, 0, and then 3 root 10 minus 2 root 10 is just root 10. And so I'm claiming that this, when you take the projection of that, the scalar projection of that onto A, you get 2. So let me check it. What is the component of B onto A? And is it 2, right? So let's do this computation, right? A dot B over magnitude of A. All right, and is that equal to 2? So A dot B. So we do 3 root 10, 3 times root 10. So we get 3 root 10, and then plus 0 times 0 doesn't matter. Then negative 1 times root 10 is negative root 10, so minus root 10. Over the length of A, but we did that earlier, that was root 10. Question is that equal to 2? Well, 3 root 10 minus root 10 is 2 root 10 over root 10. Is that equal to 2? Root 10's cancel, check. So it works. So there's an infinite number of answers I could have here. I mean, I could have changed this B2 to a 1, it would have worked. I could have changed the B1 to 5 and then worked through and figure out what this is. So infinite number of answers. This is one specific answer. Okay, 36, last problem. Suppose A and B are non-zero vectors. Under what circumstances is component of B onto A equal component of A onto B? So for 36, I think I'll do part A. I'll leave you to do part B. So given two vectors, A doesn't tell you if they're in two-dimensional or three-dimensional space. It's saying when is the component of B onto A equal to the component of A onto B. So when is that true? Well, let's just write down the definitions here. This right here means A dot B over magnitude of A. When is that equal to? This one means B dot A over magnitude of B. Well, what we know right now is that A dot B equals B dot A. So it doesn't matter, dot products are commutative. So the numerators are equal. So I can basically divide through, right? I can divide through or multiply through by 1 over A dot B. And now I'm kind of assuming something here. Right now I'm assuming that the dot product's not 0, or else I can't do this, right? So if A dot B is not 0, right, then I can cancel them out and I get 1 over magnitude of A must equal 1 over magnitude of B, which means that the magnitude of B must be equal to the magnitude of A. So if they have the same lengths and the dot product is not 0, so if the dot product is not 0 and the vectors have the same lengths, then the component of B onto A and A onto B should be the same. Does that make sense to you? Let's say that we have two vectors, okay? And let's do it in two-dimensional space so it's easier. And let's just say you take some vector. Here it is, okay? And now I come up with another vector that is, the dot product is not 0, so they are not perpendicular. So I cannot do it like a right, I can't do this, okay? I can't make a right angle. So assuming I cannot make a right angle, then I'm saying that the lengths have to be the same. So let me make, I don't know how long this is. Let me make this a little more accurate. I'll make this exactly one of these pins. And then I'm going to do another pin, so somewhere around there. All right, so if you project this one onto the red one, you get some length here. But if you project the red one onto the blue one, you're going to get the same length. So these two lengths are the same. So the component of B onto A is equal to the component of A onto B. That'll happen when the original vectors' lengths are the same, so long as they weren't perpendicular. Now, what if they are perpendicular? Okay? What if they are perpendicular? Well, if they are perpendicular, right, then this side is 0 and this side is 0, top and bottom, top here and top here is 0, and we would have equality still. The only thing we have to be concerned about is, do we have division by 0? But the problem says assume that A and B are non-zero vectors. So the length of A and the length of B can't be 0. So what we're saying now is this, that and originally we had said if the dot product isn't 0, then the lengths have to be the same. Now what we're saying is this actually doesn't matter, because if they are 0, right? If they are actually 0, then these two are equal. So we kind of have two different things. We have this. We have this. So when are those two the same? So when does the component of B onto A equal the component of A onto B? Well, if the magnitude of A equals the magnitude of B, or if A dot B equals 0, so if they're orthogonal. That's the two ways it'll happen. Now let me look at the orthogonal case. Let's say we come back in here and I draw a vector. And then I draw another vector that's orthogonal to it, which would be over here. Something like that. And notice they don't have the same lengths. Doesn't matter, because when I take this blue one and I project it down to the red one, I have to come straight down. So it's the 0 vector. And the same thing, if I project this red one down to the blue one, because it's orthogonal, it's going to be the 0 vector. So they will be equal. The components will be the same. So there's two different ways it could happen, right? It could happen if the lengths of the two vectors are the same, or it could happen if the dot product of the two vectors is 0. All right, I'll let you do part B, and that wraps it up for the homework for 10.3.